Welcome back to the deep dive. Today we are effectively leaving the safety of the harbor and sailing to the most terrifying, confusing, and absolutely fascinating waters known to science.
That's a good way to put it.
We are talking about the ultimate monsters of the universe. We're talking about black holes.
Hmm.
And I have to say, just looking at the stack of research we have for this one, I mean, we've got heavy theoretical physics chapters, historical letters from the 1700s, biographies of geniuses, and some surprisingly funny stories about gambling physicists.
Right.
This is going to be a massive journey.
It certainly is. And you use the word monsters, which is very evocative. But my goal today is to, try and push past that sci-fi caricature.
Put your cosmic vacuum cleaner.
Yeah, exactly. We all have this image of the dark drain in the bathtub of the universe, but when you actually engage with the source material, black holes are so much more than that. They're scientific realities that challenge everything we think we know about time, space, and the structure of reality itself.
Exactly. It's where the rule book of the universe essentially just catches fire. And I think the best place to start is with the name itself, black hole.
Yeah.
It feels very modern, right? It feels like something that belongs on a Star Trek poster or, I don't know, a Pink Floyd album cover.
It does feel very mid-20th century. And the name itself is. The term black hole was coined in 1969 by the American scientist John Wheeler.
John Wheeler. Okay.
It was a brilliant bit of marketing, honestly. It was a graphic, catchy description that stuck in the public consciousness immediately.
1969, the year we walked on the moon. So it feels like this discovery belongs to the space age.
The name belongs to the space age, but, and here's the first massive surprise from our research stack, the actual concept. The idea of a star so heavy that light itself cannot escape.
Yeah?
That idea isn't from the 1960s. It's over 200 years old.
Get out of here. Really? Over 200 years? Okay, let's unpack this because this just blew my mind. You were saying that while the American colonies were, fighting the Revolutionary War, someone was already theorizing about black holes.
Essentially, yes. We have to transport ourselves back to 1783. We're in England. We are looking at a paper written by a Cambridge Don named John Michell.
John Michell.
He published it in the Philosophical Transactions of the Royal Society of London. Now, to understand how he got there, you have to remember the context. This is the era of Isaac Newton.
Right, the apple falling on the head, gravity as a force, EFMA, all that good stuff.
Exactly.
Yeah.
And Newton favored a specific theory about light. He believed light was made of particles. He called them corpuscles. Think of them like tiny, tiny bullets.
Okay, so in this view, light isn't a wave like sound. It's a physical object, something with mass, just moving incredibly fast.
Precisely, like a little cannonball. And that was the seed of John Mitchell's genius. He started with a simple thought experiment. He thought, okay, if gravity affects a cannonball, slowing it down as you fire it upward, and if light is just a tiny cannonball, then gravity should affect light too.
That makes perfect logical sense. I mean, if you throw a ball up, gravity pulls it back down. If you shine a light up, why wouldn't gravity pull it back down?
Right. So Michel started calculating escape velocity. If you fire a cannonball fast enough, it escapes Earth's gravity and goes into space.
Right, about 25,000 miles an hour.
Michel asked, how massive would a star have to be so that the escape velocity required to leave its surface is higher than the speed of light?
He's asking, how big does the prison need to be so that even the fastest thing in the universe can't break out?
Exactly that.
Oh, yeah.
And he did the math. He calculated that if you had a star with the same density as our sun, but with a diameter about 500 times larger, the gravity at the surface would be so immense that those light corpuscles would try to shoot out, but they'd just be dragged right back down to the surface, just like a stone thrown in the air.
So the star's burning, it's creating all this light, it's a funness of furious energy.
Yeah.
But from the outside, you see nothing.
Absolutely nothing. The light never reaches you. Michel realized that to an outside observer, this massive object would be completely invisible. He called them dark stars.
Dark stars. I have to be honest, I almost prefer that to black holes. It sounds so mysterious, the dark star.
It does, doesn't it? And Michel went even further. He suggested that because the universe is so vast, there might be a huge number of these dark stars out there. We wouldn't see them directly, but we might be able to detect them by their gravity. By watching visible stars orbiting around an apparently empty spot in space.
That is wildly ahead of his time. He basically predicted modern black hole hunting methods in 1783. So did the scientific community jump on this? Did everyone just start hunting for dark stars?
Well, not exactly. A few years later, the famous French scientist Marquis de Laplace proposed the exact same idea. independently.
Okay.
And here's a fascinating little historical nugget from the research. Laplace included this dark star concept in the first and second editions of his absolute masterpiece, The System of the World.
So it's in the textbooks, it's official.
It was. For a while. But then in the later editions, he just deleted it.
He deleted it. Why? Did he lose his nerve or something?
It wasn't about nerve, it was about the shifting tides of scientific consensus. You see, in the early 19th century, the wave theory of light became the dominant view. Experiments showed that light behaved like a wave, not a particle.
And waves don't have mass.
Exactly. If light is a wave, like a sound wave moving through the air, it's not clear at all why gravity, which pulls on mass, would have any effect on it.
So it seemed ridiculous to treat a light wave like a cannonball.
Right, so the whole idea of the dark star suddenly looked like bad science. An interesting but flawed thought experiment.
So it got shelved.
Completely. It just vanished from the scientific literature. It was treated as a historical mistake.
That is classic science history, isn't it?
Yeah.
The core idea was right, but the theory behind it fell out of fashion, so the whole concept just got buried for a century.
Exactly. It sat in the dark, so to speak, until 1915. That's when Einstein published his general theory of relativity. And that changed the whole game, because Einstein showed that gravity doesn't just pull on mass. Gravity warps the very fabric of space and time itself.
So Einstein resurrected the dark star, but he gave it a whole new rule book.
He built the modern foundation for it. He showed that even if light has no mass, it still has to travel through space. And if a massive object curves that space, well, the light has to follow the curve.
And if the curve is steep enough, the light just falls in.
It has no other choice.
Okay, so we have the theory back on solid ground. But having a theory is one thing. Actually making one of these things is another. Nature doesn't just build black holes for fun. They're the leftovers, right? They're the corpses of stars.
That's a perfect way to put it. To really understand the black hole, we have to understand the life and, more importantly, the death of the star that creates it. We have to look at the engine.
So let's look at that engine, because a star isn't just a big burning rock in the sky. It's something much, much more dynamic.
It all begins as a huge, cold cloud of gas, mostly hydrogen. Gravity, the great organizer of the universe, starts pulling this cloud together. As it collapses, the atoms start smashing into each other.
And that creates friction, heat.
A lot of heat. It gets hotter and hotter and hotter. Eventually, the core temperature hits millions of degrees, and something incredible happens. The hydrogen atoms start fusing together to form helium.
Nuclear fusion, the holy grail of energy.
Exactly. It's basically a controlled hydrogen bomb explosion that lasts for billions of years. And this is the key. That explosion releases a tremendous amount of heat and pressure pushing outward.
So you have this constant war going on inside every star.
A constant, beautiful tug of war. You have gravity pulling everything inward, trying to crush the star into a tiny, dense point.
And then you have the fusion energy pushing everything outward, trying to blow the star apart.
And for most of a star's life, those two forces are in perfect balance.
The source material uses a balloon analogy here, which I found really helpful.
It's a classic, yeah. Think of an inflated balloon. The rubber of the balloon is under tension. It wants to shrink the balloon down. That represents gravity.
Okay.
The air pressure inside, pushing out against the rubber, represents the heat from fusion. As long as those two forces are balanced, the balloon stays the size it is. The star is stable.
And our sun is in that state right now, just happily balanced.
Yes, the sun is in a stable, middle-aged state. It has enough hydrogen fuel in its core to keep that outward pressure going for another 5 billion years or so.
But here's where it gets really interesting and a little paradoxical.
Ah, yes.
The fuel paradox. I had to read this section twice. Massive stars, the big ones, run out of fuel faster than small stars. That just doesn't seem fair. If you have a bigger gas tank, you should be able to drive longer.
You would think so.
Yeah.
But in the stellar world, mass is a curse. A very short-lived curse.
Yeah.
Because the more mass you have, the stronger your gravity is. That means the rubber of the balloon is squeezing incredibly hard. To balance that immense crushing force, the star has to burn its fuel at a furious, insane rate just to generate enough outward pressure to survive.
So it's like driving a giant SUV, but you have to keep the gas pedal floored just to keep the engine from stalling under its own weight.
That's a great analogy. A massive star burns through its fuel millions of times faster than a star like the sun. While the sun might last 10 billion years in total, a really massive star might burn out in just 10 million years.
A cosmic blink of an eye.
They live fast and die young.
And inevitably, no matter the size, the fuel runs out. The engine sputters and stops. The heat turns off.
And gravity wins.
This is the moment of collapse. And depending on how heavy the star was to begin with, the story can go in a few very different directions.
Correct. The star starts to cool and contract under its own weight. And for a long time, scientists weren't entirely sure where that contraction stopped, or if it stopped at all. This brings us to a young man named Subramanian Chandrasekhar.
I love this part of the story. It's so human.
It is.
So it's 1928. He's an Indian graduate student. He's only 19 years old. And he is on a ship sailing from India to England to study at Cambridge.
Imagine that scene. No computers, no fancy calculators, no internet. Just a 19-year-old on a long sea voyage, looking up at the stars and working through incredibly complex quantum mechanics and relativity in a notebook.
That beats doing a crossword puzzle on a flight. So what did he figure out on that boat trip?
He was tackling that very question. How big can a star be and still support itself against gravity after the fuel is gone? He used a concept from the new field of quantum mechanics called the Pauli exclusion principle.
Okay, Pauli exclusion principle. That sounds terrifyingly technical. Can we break that down?
It's actually quite relatable, I think. Think of matter particles, electrons, in this case, as having a desperate need for personal space. The principle states that two electrons cannot occupy the same quantum state in the same place at the same time.
So gravity is trying to crush everyone into a cosmic mosh pit, and the electrons are basically stiff-arming each other, saying, back off, dude, this is my spot.
That is a perfect analogy. That stiff arm creates a pressure, a repulsion force we call electron degeneracy pressure, that acts like a structural support. It can balance gravity even when there's no more heat.
And that's a white dwarf.
That's a white dwarf.
Yeah.
Chandrasekhar realized this degeneracy pressure could support a dead star. And we see these all over the place. The companion star to Sirius is a white dwarf. It's incredibly dense. Imagine the mass of the sun squeezed into the size of the Earth, but it's stable.
But Chandrasekhar found a limit, a breaking point.
He did. On that boat, he combined this quantum idea with Einstein's relativity and found something startling. Relativity limits how fast particles can move. They can't go faster than the speed of light. He calculated that if a star's core is more than about 1.4 times the mass of the sun,
Which we now call the Chandrasekhar limit.
right, above that mass, the electrons would have to move faster than light to provide enough pressure. Since they can't, the stiff arm fails.
Gravity just crushes right through the defense.
Exactly. The star collapses past the white dwarf stage. And in 1928, this was a radical, almost heretical idea. It implied that for stars above this mass, there was nothing to stop the collapse. It would just go on forever.
And this is where the drama kicks in. He gets to England, he presents this groundbreaking idea, and he runs into Sir Arthur Eddington.
Sir Arthur Eddington, the authority. The man who had famously led the expedition that proved Einstein's theory of relativity was correct. A giant of astronomy.
Eddington.
Eddington absolutely hated this idea, despised it.
He publicly attacked it, didn't he? It was brutal.
He did. At a meeting of the Royal Astronomical Society, Eddington stood up and just tore Chandrasekhar's theory apart. He called it absurd. His famous quote was, "There should be a law of nature to prevent a star from behaving in this absurd way."
That is just heartbreaking. You're a 19-year-old genius, you've done the math, you've crossed the T's and dotted the I's, and the biggest rock star in your field publicly tells you you're talking nonsense.
It was devastating. It basically forced Chandrasekhar to abandon that line of work for years. He turned to other, less controversial problems in astronomy. It wasn't until 1983, 50 years later, that he finally won the Nobel Prize for that very work he did on the boat as a teenager.
Wow. But Eddington was wrong. Gravity doesn't care if a famous astronomer thinks its effects are absurd.
No, it does not. And later, the Russian physicist Lev Landau pointed out there was one more possible stopping point. If you crush the electrons into the protons inside the atomic nuclei, they combine to form neutrons.
And neutrons also have an exclusion principle.
They do. They also demand their personal space. So you can get a star supported by neutron degeneracy pressure.
A neutron star.
Right.
Huh.
And now you have a star that is even more mind-bogglingly dense. It's only about 10 miles across, the size of a city like Manhattan, but it contains more mass than our sun.
A teaspoon of it would weigh 1 billion tons.
Something like that, yeah.
Yeah.
But even that has a limit.
If the star is just too heavy, even the neutrons give way.
Exactly. If the remaining mass after the explosion is more than about 3 times the mass of the sun, there is no known force in the universe strong enough to hold back the final, ultimate crush of gravity. The collapse becomes total and unstoppable.
Enter Robert Oppenheimer.
Yes, in 1939. This is just before he went off to lead the Manhattan Project and build the atomic bomb. Oppenheimer and his student Hartland Snyder finally solved the problem of what happens to those most massive stars.
And they introduced the concept of light cones to visualize the collapse.
They did.
Okay, light cones. This is where we get deep into the bending of space-time. Help us visualize this.
Okay, imagine a flashbulb goes off right in front of you. In that instant, the light spreads out in an ever-expanding sphere.
Got it.
Now, if you map that on a graph where time goes up and space is flat, that expanding sphere of light traces out the shape of a cone. The point is the now, and the cone opening upwards represents all the possible paths light can take into the future. It's your future cone of influence.
Okay, so the cone shows you where you can go as long as you don't exceed the speed of light.
Exactly. In normal flat space, the cone points straight up and out.
Yeah.
But gravity, as Einstein showed, bends light. Near a massive collapsing star, gravity starts to pull those light paths inward. The cones start to tip.
So the exit doors are getting harder to find. The possible futures are being restricted.
Precisely. As the star shrinks and gets denser, the gravity at its surface gets stronger and stronger. The cones tip more and more inward. Eventually, the star shrinks to a critical radius, and the light cones tip over completely. All the future paths, even the ones for light, now point inward toward the center of the star.
So every possible path points inward?
Correct. There is physically no direction you can point a flashlight that leads away from the star. All futures lead to the center. This boundary, this surface where the cones flip over for good, is the event horizon.
The point of no return.
The ultimate point of no return.
I want to talk about what this actually looks like. The source material has this fantastic thought experiment about an astronaut falling in while a spaceship watches from a safe distance. It really highlights how weird time and space get.
This is one of the best ways to understand relativity's effects. So let's set the scene. Let's say you, the host, are the astronaut. You were brave, or perhaps you just lost a bet.
I lost the bet, definitely.
You were going to dive into a black hole. I am staying safely in the spaceship, far away, with a very powerful telescope.
I appreciate your support from a distance, so I'm falling, and I have a watch, a very accurate one.
And you agree to send me a signal, a flash of light from your helmet, every single second, according to your watch. Tick, flash, tick, flash.
Okay, so I'm falling toward the event horizon. What's happening to me?
To you, locally. Nothing weird. Your watch keeps ticking normally. 1 second feels like 1 second. You cross the event horizon, let's say, exactly 12:00 p.m. on your watch. You don't hit a wall. You don't feel a jolt. You just float right through.
But what do you see from the spaceship?
I see something very, very different. As you get closer to that intense gravity, from my perspective, your time starts to slow down. It's called gravitational time dilation.
So my seconds are longer than your seconds.
Yes. I see the gap between your light flashes getting longer and longer. At first it's tick, flash. Then becomes tick, flash. Then tick, flash.
So I look like I'm moving in extreme slow motion.
Exactly. And the light coming from you is struggling to climb out of that deep gravity well. It's losing energy.
So it gets redshifted.
Severely. You appear to turn red, then deep red, then infrared. You get dimmer and dimmer.
And what happens when I cross the event horizon at 12?
I never see you cross. The signal you sent at 11:5959 p.m. eventually reaches me, very faint and very delayed. But the signal you sent at the exact moment of crossing at 12:00 p.m., it gets caught at the horizon. It hovers there forever, from my point of view.
So to the entire universe outside, I am a ghost, frozen on the edge for all eternity.
Fading into blackness. But in your own reality, you've already fallen in and are heading for the center. It's two completely different realities existing at once.
That's just profoundly weird.
Oh,
Okay,
yeah.
so that's the view from the outside. But let's go back to my experience. I've crossed the horizon. I'm inside. What happens to my body? Because this brings us to my favorite scientific term of all time. Spaghettification.
It is a wonderfully gruesome term for a truly gruesome process. It's all about gravity gradients, or tidal forces.
Meaning?
We usually think of gravity as a uniform force, but it gets stronger the closer you are to the source. The inverse square law.
Right.
Now, if you are falling feet first toward a black hole, your feet are slightly closer to the center than your head is.
Sure, a few feet closer. On Earth, that difference is meaningless.
Exactly. But near a black hole, the force of gravity is changing so violently over such short distances that the pull on your feet is massively incredibly stronger than the pull on your head.
So my feet are accelerating much faster than my head.
So much faster. You are literally being stretched out.
Mm-hmm.
At the same time, because all parts of your body are falling toward a single central point, you are being squeezed from the sides.
Stretched and squeezed.
You're elongated into a thin strand of biological material.
Like spaghetti.
Like spaghetti. And eventually, the stretching force becomes stronger than the chemical bonds holding your flesh and bones together. You snap.
Okay, but, and this is a distinction I missed before reading this deep dive, this doesn't happen the same way for every black hole, does it? There's a huge difference between a stellar black hole and a supermassive one.
This is a crucial aha moment. It's so counterintuitive. With a stellar mass black hole, one formed from a single star, the event horizon is relatively small, close to the singularity. The gravity changes very rapidly over short distances, so the tidal forces are immense.
Meaning
you would be spaghettified and torn apart before you even reach the event horizon.
so I'm dead before I even get inside the club.
Long dead, yes.
Yeah.
But for a supermassive black hole, like the ones at the centers of galaxies, the event horizon is absolutely massive. It can be millions of miles out from the center.
The size of a solar system, even.
Exactly. And because you're so far from the center, the difference in the gravitational pull between your head and your feet at the horizon is actually quite small. Manageable, even.
So I could cross the event horizon of a supermassive black hole and not even feel it.
You wouldn't feel anything special at all. You'd look at your watch, it would keep ticking normally. You'd cross the point of no return without a bump in the road.
That is somehow even scarier to me. You cross this invisible line, and suddenly you can never go back to the universe you came from, but you don't even know you've done it.
Not at first. But as you continue to fall toward the center, the tidal forces will eventually ramp up, and you'll get spaghettified all the same. It just happens deep inside the prison rather than at the front gate.
The source material quotes Dante here from the entrance to hell, "All hope abandon, ye who enter here."
It's very fitting. The event horizon is a one-way membrane. You can fall in, but you can never come out. And all paths, all timelines inside, lead to one inevitable destination: the singularity.
The singularity. This is the stuff of sci-fi endings. What is it, really?
Mathematically, it is a point of infinite density and infinite space-time curvature.
Infinite. That's a word science doesn't like.
It's a word that means our theories have broken. It's where the laws of physics as we know them just stop making sense. General relativity predicts this point, but it can't actually describe it. It's the end of time itself. Just as the Big Bang was the beginning of time for the universe, the singularity is the end of time for the collapsing body and anything that falls in.
Now, this idea of a singularity, this point where predictability completely fails, really bothers scientists. They didn't like the idea that there could be these points of chaos just hanging out naked in the universe.
Right. If a singularity is naked, meaning it's visible from the outside, not covered up by an event horizon, it would mean that unpredictable chaos could radiate out into the universe.
It's like a cosmic glitch.
A glitch that could break everything. We wouldn't be able to predict the future because random, uncaused effects could just come flying out of the singularity at any moment.
So Roger Penrose proposed a solution, the cosmic censorship hypothesis.
A brilliant name. His idea was that God abhors a naked singularity.
Meaning nature has a built-in decency code.
Essentially, yes. The hypothesis is that nature effectively censors these abominations by always wrapping them in an event horizon. The horizon acts like a cosmic curtain, hiding the singularity. It protects the orderly, predictable outside universe from the breakdown of predictability happening inside.
So chaos exists, but it's locked in a box where we can't see it and it can't affect us.
Exactly. What happens in the singularity stays in the singularity.
And this, of course, led to a bet. I love that these brilliant physicists, Stephen Hawking, Kip Thorne, John Preskill, bet on the fundamental laws of the universe like it's the Super Bowl.
This is a famous one. Stephen Hawking bet that cosmic censorship would always hold, that naked singularities could not exist. He was a man of order. He really wanted the universe to be predictable.
Well, he lost, right?
He did. Eventually, researchers running computer simulations found that under very specific, somewhat artificial conditions, you could theoretically form a naked singularity.
So nature does allow it, in principle.
Technically, yes. So Hawking conceded the bet, and the payout was that he had to clothe their nakedness.
Which means, what did he have to do?
He had to buy them T-shirts. And the T-shirts had a slogan on them. Something like, "Nature abhors a naked singularity." to poke fun at the idea.
That is fantastic. I just love the image of Stephen Hawking having to go online and order custom T-shirts for his physicist buddies because he lost a bet about the nature of reality.
But Hawking claimed a moral victory in the end. It turns out those computer-generated naked singularities are highly, highly unstable.
Oh,
If you disturb them even slightly, like say throw a single photon at them, they immediately collapse and form an event horizon. So in the messy, real universe, you'd probably never actually see one. Cosmic censorship holds in practice.
okay, so the censorship basically holds. Now, speaking of what these things look like, we have this idea that stars are complicated, messy things. But the research mentioned something called the no-hair theorem for black holes.
A black hole has no hair. This is John Wheeler again with the colorful, memorable language.
What on earth does hair have to do with astrophysics?
Hair is a metaphor for details, information, complications. Think about a star that collapses. It has hair. It has mountains of plasma, powerful and complex magnetic fields, different chemical compositions at different layers, a shape that might be a bit lumpy from its rotation. It's complex, it has a history.
Right, a lot of features.
The no-hair theorem says that when that star collapses into a black hole, all that complexity is erased. It's wiped clean. The black hole settles down into an incredibly simple, perfect state. It retains only 3 properties that we can measure from the outside.
Just 3.
Just 3. Its mass, its spin or angular momentum, and its total electric charge.
That's it. So all the other information, what it was made of, what shape it was, is gone.
Gone. Vanished behind the event horizon. So if you threw a television set, a dictionary, and a rock into a black hole, once it settles down, the black hole doesn't care. It just gets a little bit heavier, maybe spins a little differently. It doesn't remember that one object was a dictionary and the other was a rock.
That is wild. It's the ultimate eraser.
And we know this thanks to the work of people like Werner Israel and Roy Kerr in the 60s. Israel showed that a non-rotating black hole must be a perfect sphere. The solution is simple.
Which makes sense. Gravity pulls equally in all directions.
But of course, everything in the universe spins. Stars spin. So Roy Kerr found the mathematical solution for rotating black holes. They bulge at the equator, just like the Earth does, but in a mathematically perfect way, determined solely by their spin and their mass.
So how does it get from being a lumpy, messy, collapsing star to this perfect, smooth object? Where does the messiness go?
It's radiated away as gravitational waves.
Ah, the ripples in the fabric of space-time.
Exactly. The source uses a great analogy of dropping a jagged, ugly rock into a perfectly still pond. At first there is a big, messy, complicated splash, but the ripples, the waves, carry that energy and complexity away, and the water surface settles down to be perfectly smooth again.
So the black hole rings like a bell as it forms.
It rings down, yes. It radiates away all its imperfections, all its hair, as gravitational waves, and what is left behind is a perfect, smooth, simple object.
It's poetic in a weird way. The most violent event imaginable leads to the most perfect, simple object.
It is a kind of cosmic simplicity.
So we have this perfect, invisible, simple object. But for a very long time, this was all just math on a chalkboard. It was theory. People didn't actually believe they existed in the real world.
No, it was a very similar situation to the dark star concept a century and a half earlier. The math worked, sure, but was it real? The skeptics argued, you can't just invent these absurd objects because your equations say they might exist. They needed proof.
So how did we go from mathematical fantasy to observed reality? How do you hunt for something that is, by definition, invisible?
You don't look for the black hole itself. You look for the chaos it creates around it. You look for the victims.
You look for the breadcrumbs.
Exactly. The first major clues came in the 1960s. Astronomers started discovering these incredibly bright but distant objects called quasars.
Right. Martin Schmidt, 1963.
Yes. He was studying an object called 3C273. It looked like a star, but its redshift, the speed at which it was moving away from us, showed it was billions of light years away.
And to be that bright from that far away.
It had to be outshining an entire galaxy of hundreds of billions of stars. But the light also flickered rapidly, which meant the object making the light had to be incredibly small, maybe the size of our solar system.
What could generate that much power in such a small space?
The only power source in the universe efficient enough to do that is gravity. The energy released by matter falling into a supermassive black hole. That was the first big hint.
Okay, so that's a hint. What came next?
Then came the pulsars in 1967.
Ah, this is a great story. Jocelyn Bell Burnell, a graduate student.
She detected these incredibly regular, rhythmic radio pulses from space. Beep, beep, beep. They were so precise, so clock-like, that the team jokingly labeled the first signal LGM-1.
LGM-1, as in little green men.
Exactly. They seriously, for a short time, considered it might be a beacon from an alien civilization.
But it wasn't.
No. It turned out to be a rapidly rotating neutron star. And this was crucial because it proved that matter could collapse to a state as extreme as a neutron star, an object just 10 miles across. If a neutron star is real, then a black hole is just one small step further down the road of collapse.
So the stage is set, and then we find Cygnus X1.
This was the smoking gun, the case closer for many people. Cygnus X1 is a star system in our own galaxy where we can see a normal, visible blue supergent star orbiting. Nothing. An empty spot.
Dancing with a ghost.
A very, very heavy ghost. By watching the orbit of the visible star, astronomers could calculate the mass of its unseen companion, and it was about 6 times the mass of the Sun.
And referring back to our friend Chandrasekhar and the neutron star limit.
That is way, way above the limit for a white dwarf or even a neutron star. It's too heavy to be anything else. It has to be a black hole.
And it's not just sitting there quietly, right? It's eating.
Oh, it is voracious. Its gravity is stripping gas off the surface of the visible star. That gas forms a disk and spirals in, like water going down a drain. As it spirals, friction heats it up to millions of degrees, and it screams out X-rays just before it vanishes.
That's how we see it. We see the death scream of the gas falling in.
Precisely.
And this brings us to yet another bet. Hawking again. This man loved to gamble against his own theories, didn't he?
Yes. In 1974, Stephen Hawking bet his friend and colleague Kip Thorne that Cygnus X1 was not a black hole.
Wait, he bet against black holes again? This is his entire career. Why would he do that?
He famously called it an insurance policy. He said that if it turned out black holes didn't exist, he would have wasted years of his life's work. But at least he'd win the bet and get a consolation prize.
That is some serious intellectual hedging. Okay, so what were the stakes this time?
This is the best part. If Hawking won, meaning no black hole, Kip Thorne had to buy him a 4-year subscription to Private Eye magazine, which is a British satirical and comedy magazine.
Okay, very British.
If Thorne won, meaning Cygnus X1 was a black hole, Hawking had to buy Thorne a 1-year subscription to Penthouse.
The men's magazine? Are you serious?
The very same.
For the articles, I'm sure.
I'm sure that was the justification. And the story goes that when Hawking finally conceded the bet in 1990, because the evidence had become truly overwhelming, he broke into Thorne's office while he was away and signed the original bet to concede. And apparently Kip Thorne's wife was reportedly not amused when the magazine started arriving in the mail.
I can only imagine. Honey, why is this magazine in our mailbox? Oh, don't worry, dear. It's for science. Stephen Hawking sent it.
But that concession really marked a turning point. The scientific community at large fully accepted that these things are real, and now we see their effects everywhere.
Not just these single stellar mass ones either. We're talking about the big ones now, the supermassive black holes.
Yes. We now have overwhelming evidence that there is a supermassive black hole at the center of almost every large galaxy, including our own Milky Way.
The one in our backyard, Sagittarius A star.
That's the one. It's about 4 million times the mass of the Sun. Which sounds huge, but that's actually small potatoes compared to something like the black hole in the galaxy M87.
Right, that's the one the Event Horizon Telescope took that famous first picture of, the blurry orange donut.
That object is 6.5 billion times the mass of the Sun.
6.5 billion. It's impossible to even wrap your head around that number.
It's an object so large, its event horizon is bigger than our entire solar system. These things are the true engines of galaxies. As matter falls into them, they can create magnetic fields that shoot out jets of particles at nearly the speed of light.
And those jets can be huge, right?
Thousands of light years long. They pump energy back into their host galaxies. They shape how stars form. They are fundamental to the cosmos as we know it.
So we have the stellar ones from dead stars and the supermassive ones at the center of galaxies. Is there anything smaller? Could you have a tiny black hole?
Well, theoretically, yes. They're called primordial black holes.
Primordial, meaning from the very beginning of time.
Exactly. We talked about how you can't make a small black hole today because small stars don't have enough gravity to collapse that far. But in the very early universe, just fractions of a second after the Big Bang, the universe was incredibly dense, and the pressure was immense.
So you didn't need a star's gravity. The universe itself could crush matter.
John Wheeler calculated that the conditions were so extreme, patches of matter could have been spontaneously crushed into black holes with, say, the mass of a mountain.
A black hole with the mass of Mount Everest compressed down to what size?
A fraction of the size of a single proton.
That is just mind-bending. Wheeler had a great analogy for the pressure required to do this today, didn't he?
He did. He said if you took all the heavy water from all the oceans on Earth and used it to build a single colossal hydrogen bomb,
Okay, I'm with you so far.
and you exploded it, the inward pressure at the very center of that explosion might be enough to compress a little bit of matter into a small black hole.
Of course, as he dryly noted, there would be no one left alive on the planet to observe it.
A minor drawback to the experiment, yes. But these primordial black holes are fascinating because we haven't found any definitive proof of them yet. But they could be out there, making up some of the dark matter.
So we've gone from these 18th century dark stars, which were a forgotten curiosity, to these modern monsters that power entire galaxies. It's been quite a journey.
It truly has. We went from a mathematical absurdity that a genius like Eddington laughed at to an observed reality that defines the large-scale structure of our universe. It's a real testament to the power of human curiosity. We set out to find the most invisible things in existence, and we found them.
And the most powerful. It really feels like, in the end, gravity is the ultimate winner. You can fight it with heat from fusion, you can fight it with quantum exclusion principles, but if you have enough mass in one place, gravity always wins.
It always does. It collapses everything to a single point.
So wrapping up, what does this all mean for us? Why should you, listening right now, care about something so far away that it would turn you into spaghetti?
I think it matters because black holes are the ultimate testing ground for our understanding of reality. They are where general relativity, our theory of the very big, smashes into quantum mechanics, our theory of the very small. They are the edge of the map. If we can ever truly understand the singularity, we might understand the origin of the universe itself.
That's a beautiful thought. But before we go, I want to leave the listener with something to chew on, something you mentioned earlier when we talked about the no-hair theorem.
The information loss paradox.
Exactly. If I throw a diary into a black hole, a diary containing all my memories, my secrets, the history of my entire life, and the black hole crushes it down to a singularity, and the black hole itself is just a simple sphere defined by mass and spin, where did the information in that diary go?
It's arguably the biggest unanswered question in theoretical physics. If that information is truly lost forever, then the universe is not just evolving, it's forgetting. The history of the universe is being slowly, irrevocably deleted.
Is the universe forgetting its own history? That is the question we'll leave you with. Thanks for diving deep with us.
Thank you. Keep looking up.